Hello everyone, I'm Akshay Malhotra and this is a virtual presentation of our work on optimizing camera placements for overlapped coverage with 3D camera projections. This work was completed at Standard AI. Standard AI develops autonomous checkout technology that allows for shoppers to walk into a convenience store, grab the items they want and walk out without having to stand in queues for billing. To bring this autonomous shopping experience to reality, the shopper needs to be continuously tracked and localized across the store environment using multiple overlapping camera views. Beyond this, the shopper's interaction with the items on the shelf also has to be constantly observed and accounted for. These underlying tracking and detection functionalities are heavily reliant on efficient camera placement to ensure unoccluded views and complete coverage of the store environment. Thus, the objective of this work is to develop an optimization framework for camera placement, which can ensure that the underlying systems and functionalities can operate with high accuracy. From a camera placement perspective, this objective translates to observing the walkable areas and the shelves in the environment with multiple overlapping views. To serve different use cases, it is possible that different regions within the environment may have different camera overlap requirements. For example, localizing shoppers may require at least 2 cameras, whereas detecting items or products on a shelf may require just 1 camera. The angle of view, or the angle at which the camera observes a specific surface, may also be constrained to observe the items in a shelf. Further, to ensure the accuracy of the view for each camera being placed, it is important to account for the 3D geometry of the environment. We pose the camera placement problem as a combinatorial optimization, where we have a large pool of potential camera locations represented by the orange dots in the top figure, and we are interested in finding the optimal set of cameras which satisfies all the coverage, view, and position-related constraints discussed before. For such an optimization, it is very important to correctly model the view of the camera or the volume of the store environment visible to a camera. To this end, we project each camera's view on the 3D point cloud representation of the environment and model the camera's view as a set of voxels visible to the camera. Next, we discuss the overall optimization framework. The objective is to minimize the difference between the desired coverage at each location in the store given by gamma j and the overlapping coverage obtained by the set of selected cameras given by the summation of camera views of the selected cameras. We further impose a budget constraint on the total number of cameras that can be selected and add any location relation constraints that may exist. Although this is a nonlinear non-convex formulation, we further propose a piecewise linear reformulation of the problem that allows us to pose this as a mixed integer linear programming problem. The details on the reformulation and the final MILP formulation can be found in the paper. Finally, here is a quick example of how our camera placement system ingests a point cloud of an environment, builds a 3D model with shelves, floor, and walls, and further utilizes the proposed optimization framework to come up with the optimal camera placement. Thank you.